Hello and welcome. In this short video, we're just going to take a look at a few important set identities. Now, there are lots of them, but most of them stem from these basic laws. In the next video, we'll take a look at how we establish some more or less solid proof, if you will, or valid logical arguments for why these things are true. But a lot of these have quite a bit of intuition. So let's take a look at least one of the identity laws here. If I take some set that we call A, and I intersect it with the universe, I am going to get the set A. So what would that look like? Well, I have some set in here. Within there, I've got a set named A, and I've got the universe here. Now, the universe covers everything inside of that rectangular box. The things that are inside of A are just things that are inside of that circle. So what two things, if you could imagine that the universe is all of this stuff and A is just the circle, if I wanted to find where those two shadings had common ground, well, you'd probably say that if you take the entire universe and you look at only the things that the universe has in common with A, that's going to just produce the set A. That's only going to produce the elements that are inside of there. So the intersection between A and the universe is just A. Now, if you, for instance here, take A and you union it with an empty set, then you're only going to get the set A. Let's think about this in terms of an example. Let's say that A is equal to some elements 1, 2, 3. And then we're going to look at the empty set, which we know that the empty set is the set that contains nothing in it. Now, the union operator says take everything that's inside of A, take everything that's inside of the empty set, put them all together in a new compartment. Well, I'm going to certainly have the elements that are inside of A, 1, 2, 3, and now I'm going to go and grab all the elements that are inside of the empty set. Wait a minute, there's nothing in there. So that means there's nothing that the empty set is going to contribute to the union, and therefore we see that A union, the empty set is just going to consist of the elements of A, and therefore A union empty set is A. Now, of course, we've got to be kind of careful with this. I mean, logically this holds regardless of what's inside of A, but we did just prove by example, meaning we just looked at an example that we're trying to make a broader conclusion about. So we have to be careful about things like that. And we'll investigate that a little bit more in the next video. Okay, so if you take all of the elements of A and you combine them with all of the elements inside of the universe, then you're going to get the universe, right? Because the universe is bigger than the set A, or at least it's at least as big as the set A. Potentially A could take up the whole universe if we define it in such a way. If you intersect A with the empty set, well, we could look at this. If we take A and the empty set and we ask what's in common between those two sets, well, the empty set doesn't have anything in it. So the things that are in common between some set A that has some elements in it and the empty set is nothing. So we're going to get the empty set. You can probably imagine that if you take A complement and you take the complement of that, you're going to get A. So it's like me saying it is not the case that I am going to the store. Okay, well, if it's not the case that I'm going to the store, that means I'm not going to the store. But it is not the case that I'm not going to the store. So that means I am going to the store. So I could have just said I am going to the store in the first place. The order in which you combine two sets via union or intersection does not matter, and that's simply what the commutative laws here are telling us, that the order in which we consider those is not important. We get into some of the associative laws. So notice the associative laws in this first example operate strictly off of unions. So there are no intersections in this statement at all, and in the intersection associative law, those are all intersections across the board. So this is essentially telling us that if I'm going to union three sets together, it doesn't matter which two sets I start with first. Again, only if those are all unions. So if I take all of the elements from B and all of the elements from C and combine them into one set, and then I take all the elements from A and combine them into that set, that's going to be the same thing as me taking all the elements in all the elements in A, all the elements in B, putting them together, unioning them, and then taking all the elements in C and adding them to that new set. Because remember, repetition doesn't matter. So if an element is already in a set, adding it from an existing set is not going to change it. And then these distributive laws, one of which we've seen in the previous video, that if I look at the intersection between A and the union of B and C, that's the same thing as taking the intersection between A and B, the intersection between A and C, and unioning them together. De Morgan's laws are really valid, are very helpful whenever you have the negation of something in its entirety. So to give a little bit of intuition here, let's take a look at a picture where we have A and B, two sets in here. And we want to look at the negation, something that is not in both A and B. Okay, so that means it might be helpful to start with what is inside of A and B. Well, what is inside of A and B is just this little football-shaped overlap, right? So if you take the negation of an intersection, if you take the negation of everything that's shaded right here, you get everything outside of that region. Therefore, the intersection, the complement of the intersection between A and B is everything not inside of that little football. So it's everything outside of that is the complement, excuse me, I think I said negation, the complement of A and B. So to be in not A and B means you're anywhere but A and B. Now let's look at this. To be in not A, and since this is a union, that means it's going to combine all of the elements. So I can just begin shading in one picture. So not in A is everything that's outside of A. Just like this. So that's everything that is inside of not A. To get everything shaded that's in not B, well, that's everything that's outside of the circle B. So that's going to be, a very, very dark color. Let's try something a little bit lighter here. That's going to be everything. That's not going to work. So everything that is not inside of B, I'll just maybe move to a pencil. Everything that is not inside of B is all of this stuff here. And now we're going to union those together. So the red kind of crazy looking pencil that I'm using here and all of the green are going to be combined because we're going to take a union, or everything that's not in A unioned with everything that's not inside of B. And so you see that the shading is identical. All right, we'll go ahead and stop there. Maybe a little bit of intuition behind this absorption law. This one says that if you union A with the intersection between A and B, you get all of A. So A and B is the intersection. That's going to be this portion here. A is everything that's inside of the circle A. And if you union just this intersection with this entire circle, you're going to combine them. Well, that means you're going to get the entire circle. So a lot of these have some really intuitive ways of thinking about them. In the next video, we'll take a look at how do we prove this with absolute certainty. See you in the next video.